In the Beginning by Dr. Walt Brown, we will take a look at the images of the continental drift phase of the hydroplate theory. I believe this is on page 140 and 140. Nope, it's on page 142 and 143. Okay, you got the springs. The spring remains aligned. And then let's see what it says at the bottom here. Okay, let's do this. Okay, A, overlying rock keeps a compressed spring horizontal. B, the spring remains aligned and compressed as the gap between the rocks widen. C, when the gap reaches a certain critical width, the spring suddenly buckles upward. Now consider thousands of similar but parallel springs lined up behind the first spring, all linked together and repeating in unison steps A to C. Upward buckling on any one spring will cause adjacent springs to become unstable and to also buckle up. They in turn will lift the next spring and so on in a rippling fashion like following dominoes, but slowly because the mid-oceanic ridge is so massive. D, rupture completed, jettison water not shown. E, the rupture's path widens by the erosion crumbling and collapse of the unsupported vertical walls, exposing part of the chamber floor. Most of Earth's sediment, tens of millions of cubic miles of sediment, are quickly produced by escaping high-velocity waters, the fountains of the great deep. Fracture zones form perpendicular to the ridge axis, rifts from along the ridge axis. The massive hydroplates, lubricated by supercritical water, begin to accelerate downhill, As more and more weight slides away from the newly formed ridge, the exposed chamber floor quickly rises several miles, accelerating the hydroplates even more, and becomes the Atlantic floor. In the next chapter, you will see why events in the Pacific greatly steeped the downhill slope and opened up more space for the plates to slide. Okay, let's take a look at those are the springs. Let's see what's happening inside of the Earth here. Figure 69, computer animation of the continental drift phase. The top frame shows one side of the Earth at the end of the flood phase. Because the rupture encircled the Earth, a similar eroded gap existed between the hydroplates on the other side of the globe. The mid-oceanic ridge rose first in the Atlantic, hours or days before the ends of the rising ridge extended into what is now the Pacific. This caused the hydroplate to accelerate downhill on a layer of lubricating water away from the widening Atlantic and into the gap on the opposite side of the Earth. The continental drift phase ended, bottom frame. Okay. The continental drift phase ended with a dramatic compression event that squeezed up Earth's major mountain ranges. These 6 frames simply rotate the present continents about today's polar axis. Therefore, greater movement occurred at lower latitudes. Movement begins from where the continents best fit against today's base of the mid-Atlantic ridge and ends near their present locations. Not shown are other consequences of the compression event. For example, continents were squeezed and thickened, narrowing their widths and widening the Atlantic. Continents were squeezed and thickened, narrowing their widths and widening the Atlantic. Of course, regions where mountains formed thickened the most, but non-mountainous regions thickened as well. Regions that did not thicken are now part of the shallow ocean floor. While it may seem strange to think of squeezing, thickening, and shortening granite, one must understand the gigantic forces required to decelerate sliding continental plates. If compressive forces are great enough, granite deforms, much like putty on a global scale. On a human scale, however, one would not see smooth putty-like deformation. Instead, one would see and hear blocks of granite fracturing and sliding over each other, Some blocks would be the size of a small state or province. Many would be the size of a house, and even more would be the size of a grain of sand. Friction at all sliding surfaces would generate heat. At great depths, this would melt rock. Liquid rock magma would squirt up and fill spaces between the blocks. This is seen in most places where basement rocks are exposed, as in the Black Canyon of the Gunnison and the inner gorges of the Grand Canyon, shown on the next two pages, 144 and 145. Okay, the Moho. Okay, this is on page 143. Trap pockets of water, uncertain boundary, well-established boundary. That's, pilot error again. Okay, let's read this so you can see it. Okay, typical cross-section of today's continents and oceans. Notice how the Moho is depressed under major mountains and higher under the ocean floor. Although some boundaries are uncertain, most of these general characteristics are well known. Also notice that large pockets of water should be under major mountains. So that is the graphics for the continental drift phase. We're going to come back and look at that Gunnison, Black Canyon of the Gunnison River.